This video covers section 3.3, which is titled Trigonometric Substitution. And as is somewhat obvious from the title of the section, it is going to involve quite a bit of trig. And we're also going to be doing the substitution method as well. We're going to be using those principles that we've learned from past classes. Most of the integrals that we will be looking at in this section look like one of the three forms that you see here in the introduction. They usually involve square roots, which we know from past experience, integrals involving square roots can be tough. We saw that in, I think it was the section 2.4, I believe, when we were doing arc length, because arc length has a square root in it, and a lot of times we just said, oh, go ahead and use technology to evaluate, but now I'm going to show you some things that will allow you to be able to evaluate some of those. And so this section does start out with a warm-up, and it asks you to simplify some square roots that involve trig inside. And so if you can simplify expressions like this, that is kind of part of the battle of this section. You'll notice that those three examples, A, B, and C in the warm-up, they kind of resemble the three different expressions that I underlined up here in the introduction. So let's go ahead and jump in here and start simplifying these. So in the first one, if you were to notice that both terms have a 9, so we could factor a 9 out, which leaves 1 minus sine squared. And then remembering our Pythagorean identity, which says sine squared plus cosine squared is equal to 1, that would mean that 1 minus sine squared is cosine squared. So we can rewrite this as 9 times cosine squared theta. And now, because it doesn't have that minus in there, now we can take the square root, because the square root of 9 is 3. And the square root of cosine squared theta is cosine theta, as we would normally think about it, but it's actually the absolute value of this. So it's the absolute value of cosine theta. And that's because we need to kind of think about this in terms of the original definition of the square root function. So a lot of times this is glossed over, but it is going to be important in this section. Let's remember something from algebra. So back in algebra, when we define the square root of x, it's actually not defined as x. It's actually defined as the absolute value of x. And that's because the absolute value of x can either be equal to x or negative x, depending on if x is positive or negative. It's equal to x if x is greater than 0, or greater than equal to 0, we could say, and it's equal to negative x if x is less than 0. So it really depends on whether or not what we have inside there, whether or not it is positive or it's negative. So we'll jump that road, we'll cross that bridge when we need it, and probably the first example we'll need to talk about that, but just keep that in the back of your mind. So go ahead and pause the video real quick, and I'd like you to do B and C on your own. Go ahead and simplify those. All right, so welcome back. Hopefully you were able to get to the answers that I have showing here in parts B and C. For part B and C, you need to use the other version of the Pythagorean identity, which of course says that if you take tangent squared theta plus 1, that's equivalent to secant squared theta. And you can kind of manipulate that and use it in different ways. So let's go ahead and look at example 1. We're going to jump in here and we're going to integrate an expression that involves this first type. So when you have the square root of a constant squared minus x squared. Notice that what you see here in example 1 has that same form. And so I'm going to start by rewriting the integral. So we have the integral of the square root of 1 minus x squared dx. And notice that up here in the warm-up, because it has that 1 minus, that constant minus x squared, it's going to lend itself well to the identity that involves sine squared and cosine squared. So that's exactly what we're going to do. We're going to use that identity, and we're going to do what's called a trigonometric substitution. So let's go ahead and write that in over here on the side. We're going to use a trigonometric substitution. And for that, we're going to let x equal sine theta. Because if x equals sine theta, and we were to plug that sine theta over here in for x, then we're going to get something that looks kind of like what we did here in the warm-up of part A. And we know it'll be something that will be easy to simplify, right? So let's go ahead and do that. Let's go ahead and do that. And then we know when we do substitution, we need to go ahead and find what dx is. So that would make dx equal to the derivative of sine, which is cosine theta, d theta. And then we're also going to do some of our simplifying over on the side. So much like we did in the warm-up, we know that our square root is equal to 1 minus x squared. That's the square root that's in the problem over here, right? So we want to do that, and we're going to plug our substitution into that. And we're doing this over on the side just so that we're not having to rewrite the integral and the dx every time. We're just going to do it on the side and take care of it, and then plug it back into the other side, into the integral in one fell swoop. So plugging in x equals sine theta, that gives us the square root of, instead of 1 minus x squared, 1 minus sine squared. And we know that sine squared is equal to 1 minus sine squared is equal to cosine squared. And the square root of cosine squared, as we said last time, it's going to be cosine, the absolute value of cosine theta. So let's have a little bit bigger discussion about this now, okay? So without limits, this is an indefinite integral. Without limits, we don't know if cosine is positive or negative. Without limits, we don't know if cosine is positive or negative. We do know that cosine does oscillate back and forth between -1 and +1, but we don't know what range of values we're dealing with here. So in that case, if we have an indefinite integral, we're just going to assume. So we will assume that it's positive. We will assume that cosine theta is positive, and that of course means we can drop the absolute value bars. So, and we can drop the absolute value. All right. So we're just going to rewrite this then as cosine theta. Okay, great. So going back to our original problem, this integral can be rewritten because we just saw that the square root of 1 minus x squared is equal to cosine theta. And then we know that dx is equal to cosine theta d theta. So again, let's label these. This right here, oops, sorry about that, it's jumping all over the place. This right here is equal to square root of 1 minus x squared. This right here is dx. Okay, hopefully that makes sense to you. Let's go ahead and simplify this. So this is equal to then the integral of cosine times cosine is cosine squared theta, which takes us to our last section, right? We saw in the last section that when we have an even power of cosine, we want to use a trig identity. In this case, the half angle identity. So when it's cosine squared, we get 1/2 times 1 plus the cosine of 2 times the angle. Let's go ahead and write that identity over here on the side. Right, so that's the identity we're going to use, and that allows us to find the integral now with a little mental substitution, a little mental u substitution. We can have 1/2 times the antiderivative of 1 is, I don't need to rewrite that integral symbol. The antiderivative of 1 is x, and then plus a factor of 1/2 times the sine of 2 theta plus c. And we can go ahead and, I did make one mistake there. I just noticed this should not be an x. What should that be? That should be a theta. Then we can go ahead and distribute in the 1/2 there. That gives us 1/2 theta plus 1/4 times the sine of 2 theta plus c. And now that looks great. The only issue is this answer is in terms of theta, and we know our original integral was in terms of x, so we need to get everything back in terms of x, and the way we do that is with a right triangle. So we're going to use a right triangle to go ahead and convert everything back to being in terms of x. Let's go ahead and write that down. Use a right triangle to convert our answers back in terms of x. So what do we mean by a right triangle? Well, I don't know how much you remember from pre-calculus. It's not everybody's favorite subject, doing right triangle stuff, but let's go ahead and draw in a right triangle. So we have a right triangle here, which of course it means it has a 90-degree angle. Let's assign one of these angles as theta. And we know that in our original substitution, which is up here, we let x equal sine theta. So we're going to bring that x equals sine theta down. We're going to use that. So if x is equal to sine theta, let's actually write it the other way. I think it will be more useful to us. Let's write sine theta is equal to x. And remember, we usually think of sine in terms of opposite over hypotenuse. That's SOHCAHTOA. And so we want to think of this as a fraction. So instead of x, we'll rewrite it as x over 1, where the top would be the opposite side, right? The top is the opposite, and then the bottom, the 1, is the hypotenuse. So that's because sine theta is equal to the opposite over the hypotenuse. Simple trig there. And so, that being the case, on our right triangle, if sine theta is equal to x over 1 and x is the opposite, that means this side over here, the right triangle, that's the opposite side, has to be x, and the hypotenuse then is the long side across from the 90, that's got to be 1. And then that also tells us what this other side is. We can get that from the Pythagorean theorem. It tells us that side must be 1 minus x squared. This comes from the Pythagorean theorem. And that missing side, I've never seen an example where it isn't. It's almost always going to be that square root that we started with. So we started with the square root of 1 plus x squared up here, right, in the original problem. That's always going to be what that other side is when you solve for it using the Pythagorean theorem. All right, great. So we're pretty much there. Let's go down and rewrite our answer now. So this is equal to 1/2. Okay, the first thing we need to do is figure out what theta is, and that's fairly easy to do because, and again, this is more trig, so we know that x is equal to sine theta, or sine theta is equal to x, which means that theta is equal to the inverse sine of x. And that's just taking the inverse sine of both sides to get theta by itself. So we have, instead of theta here, we have the inverse sine of x plus 1/4 times sine 2 theta. And so our right triangle down here is in terms of theta. We're actually going to need to rewrite that. And so we can use a trig identity there. There's a trig identity that says that the sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. And so we can rewrite this as 1/4 times 2 sine theta cosine theta plus c, which gives us 1/2 times the inverse sine of x, and 1/4 times 2 is 1/2. And now we use our right triangle. So sine theta, we already know sine theta is x, but then cosine theta is adjacent over hypotenuse. So the adjacent side in our right triangle is right here. The square root of 1 minus x squared over our hypotenuse, which is 1. Or it's just going to be the square root of 1 minus x squared. And so we have, instead of cosine theta here, we have the square root of 1 minus x squared plus c. And that's going to be our final answer. This is our first example of performing a trigonometric substitution. Every time we're going to have to draw that right triangle to help us turn our answer back in terms of x. And that's going to do it for this video. Let me know if you have any questions. Thank you.